Okay, so just remember that so far, like I said, we've been dealing with quadratics and they're degree 2, right? Everybody, quadratic degree 2. We always look at the highest degree. Hi. Oh, hey. Okay, just have a seat wherever today. Yeah, and grab a yellow worksheet, please. Thanks. Okay, so we've been dealing with welcome, by the way. Degree 2. So we always look at the highest degree, so we know this is degree 2. So question for you: how many solutions would we have? We have 2 solutions, and when we find those solutions, guys, what you're finding is where it crosses the x-axis. Interesting, okay? Where it crosses the x-axis. But today we're going to be dealing with much higher than degree 2 and degree 2. So today we're going to be talking about end behavior of all types of graphs. End behavior. Okay, so what we're doing is we're going to be looking at the very ends of the graphs and determining what's happening there. Looking at different types of graphs, not just quadratics. We're going to look at the ends, and at the very end, see what's happening. So these are the things that you're going to describe them as. You're going to look at the ends of the graph, and you're going to describe it as up and up. You can describe it as down and down. You can describe it as down and up, so down and up. And then you can describe it as up and down. Now, these are the words we're going to be using today to describe end behavior, the very ends of our graphs and what they're doing. We're going to be looking at quadratics along with many other higher order polynomials and their functions, okay, and their graphs. Because I already have those words down at least. Okay, a couple more seconds. So up and up, down and down, or down and up, and then up and down. Now here's the important thing as you're finishing those up. You always have to look at your eyeballs from left to right. We read from left to right a book, so end behavior works the same way. We're going to be describing it from left to right. That's super important because if you describe it from right to left, you won't get it correct. You might have the correct idea in your head, but it's not correct unless we are talking left or right. Okay. So these are some examples of up and up. So looking at this, guys, looking at these functions, it's kind of interesting. This is a quadratic function. It's a smiley face. With quadratics, we either have smiley faces or frowny faces, nice round things here, U shapes. Now notice this end behavior is from left to right, up and up. Does everybody see how that's up and up? Looking at this is actually like a 4th degree polynomial. Notice it has end behavior up and up. Now look at this crazy one, squigglies in between. Well, it doesn't matter what happens in between, it still has end behavior up and up. Does everybody see how up and up looks like? Okay, let's look at a few that look down and down. So looking at this parabola here, this quadratic, it has down and down end behavior from left to right, down and down. Once again, it doesn't matter what's happening in between, the end behavior here is still down and down. Crazy function still has down and down behavior. Does everybody see that? The in-between doesn't really quite matter. The end behavior will work the same when we get to the rules. So these are just some examples. So right now, you don't have to be taking notes on this part, just looking more so you can see what it looks like. All right, this is end behavior down and up. Looking from left and right, this line, notice this line has end behavior down and up. Does everybody see that? Looking at this, it doesn't matter that it's kind of, this is actually a cubic function, but it still has end behavior down and up. Does everybody see that? Once again, in between squiggly lines, it still has end behavior down and up. Then up and down. From once again, now this is a negative line. If you were to get on the line and slide down, or like step on it, gravity would pull you down and be like sliding down a slide. Now notice from left to right, end behavior is up and down. Looking at this, it's a cubic function again. This has end behavior up and down. From left to right, squiggly in between, doesn't really matter. Still has end behavior up and down. Does that make sense, everybody? Okay. No questions on how that works, okay? Now, it was easy to see if you were given a graph, right? You were able to look at it and say, okay, it has up and up behavior. It has down and down. But we're not always going to be given a function that you can graph and look at the end behavior. So you have to know the rules. You have to know these rules. Now, a lot of times, yeah, I'm going to suggest, why not just grab it on your graphing calculator and look at the end behavior? That's the easiest. But at times, on an ACT, I have seen this. On an end-level test, I have seen this, where they give you something that doesn't give you enough information to graph. They want to know that you know the rules. So here are the rules. Here we go. Here are the rules that apply. Okay, so this is where you want to start taking notes right here. So this stuff right here. So before I start saying this, just know it doesn't matter what happens in between. I showed you squiggly lines in between. End behavior will work the same if it has these key characteristics. Okay, now note, the leading coefficient is what matters. Once again, the leading coefficient is the only thing that matters. The leading coefficient means the leading term, the leading coefficient, that's what we look at to see what our end behavior. Now, anything that comes after that does not matter. The end behavior will all work according to the leading coefficient. So you'll always look at the very highest degree. Okay? So if we have some polynomial x raised to the n power, and n is an even degree, n is even numbers, guys, 2, 4, 6, 8, 10, 12, right? You guys all know what even is? Yeah, okay? Even degree. Then it's going to have the same end behavior, meaning the end behavior is either going to be up and up or down and down. The same. It's going to have the same end behavior. So does everybody understand? If you look at this and see it's even, you know it's going to be the same end behavior, either up and up or down and down. Are we all okay to there? Yeah or no? Yes or no? Okay. All right, and then after you decide, okay, it has the same end behavior, it's either going to be up and up or down and down, you'll look at the sign in front of the leading coefficient here. So you're going to look at the sign in front. If it's a positive, it's not going to have a positive sign, but it's going to be a positive number or just a positive 1 in front. So you'll look in front. And if you look in front and you see a negative, then it's going to be down and down. So if you look in front and it's positive, then it's going to be up and up. And the way to remember it is we know that end behavior works the same for any type of function. So if we know quadratics are even, right? Are quadratics 2? Degree 2, guys. Is that an even number? Yes. And then if it was just like, for example, x squared. In front of x squared is a positive number. It's just positive, right? So we know that that's going to be positive. It's a smiley face. Positive people smile, so up and up. So that's a way to help you remember. Does that make sense? Positive people smile. It's a smiley face. And behavior is up and up. And this will be true for any even degree with a positive number in front. So looking at this, 2x to the 4th. The first thing you check is the even degree. Does everybody see how 4 is an even degree? So we know it's either going to be up and up or down and down. Then look in front. Is it a positive 2 or negative 2? Yes.
You know where Mrs. Destrup's lab is? Chemistry lab?
Does anybody know all that? It is upstairs. Okay.
The lab is upstairs.
Yes, I guess.
Upstairs at the very end.
At the very end.
So go up and then it's
This way. Yeah. Thank you. Okay, so once again, guys, this is an even degree and it's a positive 2. So I think, okay, I know it's up and up. It's a smiley face. So up and up. Okay. Any questions on that? Now, a 4th degree doesn't look like a parabola. It has some weird stuff in between, but the end behavior will work the same. Now, once again, if you decide it's an even degree, you say, okay, it's either up and up or down and down, and you look in front. If you see a negative, then you know it's going to be down and down because they like to frown. Down and down, it's negative. Negative people frown. That's an easy way to remember it. Does everybody understand how that works somewhat? We'll practice it in a second more. So an example of this would be negative x squared. Once again, you're like, okay, it's positive, it's an even degree, so it either has up and up or down and down behavior. You look in front, it's negative. Negative people frown. So this is going to be down and down. Okay, so those were just some examples. Another example would be negative 2x to the 4th. Even degree, we know it has same end behavior. It's frowning because of the negative in front, so it's going to be down and down. Okay, so now we'll go on to odd degrees. Now, once again, if you look at this and you look at the degree and it has an odd degree. So that would be 1, degree 1, degree 3, degree 5. It's odd, an odd number. 5, 7, 9. Anything that's an odd number, you say, okay, I know it has opposite end behavior. So they don't have the same end behavior. It's either going down and up or up and down. So once you've decided, okay, it doesn't have the same end behavior, it has opposite end behavior. It's either going to be down and up or up and down. What you'll do is you'll look in front. Once again, look at the coefficient in front. Out here in front. If it's positive, then it will be like a line. Now remember, end behavior works the same. A line would be considered a odd degree, right? X to the 1st. 1 is odd, true? True, and end behavior works the same for all odd functions. And we look in front here, and we see it's positive. So in this case, it would be positive 1. So we know that it's going to be like a positive line. Does everybody see how that's a positive line? Now you can use that knowledge of end behavior for all functions that are odd and positive. Positive in front. So the end behavior will be down and up, just like a positive line. So if you think, okay, this is going to be like a positive line, that end behavior is down and up. So an easy way to remember. And then looking at a negative line, once again, if you decide, okay, it has opposite end behavior because it's an odd degree, and then you see a negative in front, such as negative x to the first, you say, okay, it has opposite end behavior and it's negative, so it's going to work like a negative line. Negative lines start like this and go down, so that's end behavior up and down. So that's a way to help you remember it, hopefully. So get those rules down, and then we'll practice this, okay? Now, a lot of times you can use your calculator to graph it and just look at the end behavior, but at times you can't. You've got to use these rules, so that's why I'm teaching you them. Okay, ready to go. Here we go. First example. What is the end behavior of the function? 2x to the fourth plus 3x plus 2. 2x to the fourth plus 3x plus 2. Once again, the most important thing is the leading term, the leading coefficient. That's all we need to look at. Anything after that doesn't matter. So let's do it without graphing, using those rules. Looking at this, first of all, the first thing we look at is the degree. Is that even or odd? So it's even. So is it going to have same or opposite end behavior? So it's going to have same end behavior. Okay, so it's either going to be up and up or down and down. Now look in front. Is that a positive or negative? Positive. It's a positive. So it's going to be similar to a parabola's end behavior. So looking at that, it's up and up. Is that true? Right, up and up. Okay, so up and up. That's our answer. Now we didn't even have to graph it, but let's quickly learn how to graph it so that we can know how to check our answers. So pull out your graphing calculators real quick so that you can make sure you're good to go with graphing this. Okay, so looking at my if you don't have a graphing calculator, look up here and watch me do it. And those of you that have one, you should follow me through it. So look at right up here is the y equals key. Hit y equals. And then we're going to type in that function. So it was 2x to the fourth. So I'm going to type in, did everybody see how I got to y equals? So I'm going to type in 2. And then right here, up here is the x in the, like you can see, x, t, e, or whatever. So hit 2x. And then to raise it to the fourth, you have to use the caret key. This is caret 4. So that's 2x to the fourth. And then it was plus 3x. So plus 3x. Are we all at following? Okay, and then it's plus 2. Now, if I hit graph, so right up here, notice the key is graph. I hit graph. Looking at my end behavior here, it's going that way and that way, so it's going up and up. Is that true? It's not a parabola. Parabolas are perfectly symmetric, but end behavior works the same. So we used our knowledge of what a parabola would look like, and it did work the same. Is everybody okay with that? Okay, awesome. Okay, let's do another one really quick. Now, you didn't have to graph it. It was just so that it kind of looked kind of like that. So we do know it was up and up. Okay, let's do another one. Negative 3x cubed minus 3x squared plus x plus 2. Now, what matters is the leading term, the leading coefficient here. So first of all, is the end behavior going to be the same or opposite? It's going to be opposite. It's odd, odd, opposite. Okay, so it's going to have opposite end behavior. Okay, we know it's going to have opposite end behavior, and then we look in front. We look in front. It's negative, right? Now, we know that lines have opposite end behavior, and a negative line would look like this, true? What's my end behavior of a line? Of a negative line? What is it? Look at it. I just drew it. Up and down. So this will work the same way. End behavior will work the same. If it's an odd function, and it has a negative in front, it's going to have the end behavior the same as any other odd function with a negative in front, so up and down. Now you could check it by graphing it. So if you did graph it, I'll just graph it. This is what it would look like so that we can have some practice looking at. If you graphed it on your graphing calculator, this is what it would look like, up and down. Questions on that? Now this one, no questions on that, you're sure. Okay, now this one, this is where the one I have seen on the ACT, this exact problem. And I've seen it on an end of level similar. Okay, so looking at this, it says, given f of x is equal to negative a x to the n plus bx plus c, where n is an even degree, what is the end behavior? So I'll let you get that down. When f of x is equal to negative a x to the n plus bx plus c, where n is an even degree, and we're going to have a quiz on this on Friday, right? We're having a quiz, and I can guarantee there'll be one like this. Where n is an even degree, what's the end behavior? So we've got to look at this, piece by piece. Okay, so it says right here, where n is an even degree. So this n is an even. So what will we know about the end behavior? It's going to be the same, Very good. So we know it's the same end behavior. Very good. So it's either up and up or down and down. Now looking in front now, we have a positive or negative. Negative. So it's a frown, right? So it's going to be down and down. Questions on that one? Okay, moving on, and then I'm going to set you free in just a second. Last couple things. Now we have to get a little bit more advanced thinking in our thoughts here in secondary 3. I'm preparing you to go on to be successful in pre-calculus, which will then in turn make you successful in calculus. Looking at this, for example, looking at this function, we are being asked the same thing. What's the end behavior? So it could be worded one of two ways. Now on an ACT or on an end of level, they expect secondary 3 to be able to word it. Besides up and up, they want you to be able to word it in this kind of notation. So I call it calculus notation. Don't let the word calculus scare you though. I'm going to go through it with you and it will make sense. Domain and range made sense to you guys, right? So this will make sense to you. Okay, so looking at this one, we have f of x is equal to 3x cubed plus 2x squared plus 2. If we're talking end behavior, the only thing that matters is the leading coefficient here, the leading term. So first of all, we know for sure if we were to graph this, we could graph it and look at it. We could say it in words that this end behavior is what? Down and up, down and up. Does everybody see how in words this is down and up? Okay. Now we have to be able to word it in calculus notation, which is this, okay? So now it's saying, okay, well first of all, we could have thought through it too. We could have said, okay, we know it has opposite end behavior, and then it's positive, so it's like a positive line. So it has down and up end behavior, which is what we said. But I also graphed it, okay? So now it's going to ask it like this. Pay close attention to what I'm saying. So it says, as your x values are approaching negative infinity, what's your function approaching? I'm going to read that again. As your x values on your xy chart, as x is approaching negative infinity, as it's growing to negative infinity, your function is approaching what? Your function is growing to where? Once again, your function is growing to where? So let's focus on a second. As x is going to negative infinity. Guys, these are your x values. Does everybody see how these are x values? Now right over here, clear over here is negative infinity on my x's. As x is getting closer to negative infinity, growing this way, where's my function growing to? Where's it going to? On the y-axis, guys. Where's it growing to? Negative infinity. Very good. So negative infinity. Does everybody see that? My function's growing towards negative infinity. Okay, so don't let it get to you. Just read it how I'm reading it. Okay, now as your x values are approaching positive infinity, as your x values are approaching positive infinity, where's your function growing? Where's your function growing? So now look at your eyes. Look with your eyes. As our x values are growing that way to positive infinity, as it's going this way, where's our function growing? Positive infinity. This is how it would most likely be worded on the ACT and end of levels. I saw this exact problem on the end of levels this year, and I saw one very similar, like I said, on the ACT. Does that make sense, everybody? That looks scary, but was it scary? The wording? No, it wasn't too bad. Let's do one more example like that, and then I'm going to set you free to work. Okay, let's say our end behavior. So given this function, negative 3x to the fourth plus 2x cubed plus 2x plus 1, I chose to graph it and look at it, or I could just think about it, but I chose to graph it. Okay, it's easier to see the end behavior if you graph it, if possible. So looking at this, we know it has the same end behavior, and then it's negative in front, so we know it's a frown. So it's going to be down and down. In words, it's down and down. And I graphed it, and you can see what it looks like. Okay, so now let's do it in calculus notation. So as x is approaching negative infinity, once again, as your x values are approaching negative infinity, where's your function growing to? Good, negative infinity. That's true. All right, as x is approaching positive infinity, as your x values are growing that way, positive infinity, where's your function growing to? That way. Good, negative infinity again. Does everybody see how that works? Okay, you guys are smart. You are all very smart people. All right, so now I'm going to have you do problems 1 through 3 on the worksheet. Ready, set, go. Ready, set, go. I'll leave this up so that you can refer back to it. Just ready, set, go. Okay, so now we're going to shift gears kind of somewhat and talk about some other things here. So think about what we've been doing so far, guys. Guys, we've been taking the quadratic equation, we've been solving for the x-intercepts, we've been solving for the zero, solving for the roots. Now these all mean the same thing, guys, and that's why I'm going to say it all the time, so that you guys get used to seeing those different words. Because I have people like in secondary 3 always get to a test and they're like, find the zeros, what the heck is that? It just means x-intercepts, where it's crossing the x-axis. Or on a test we'll say, find the roots, and they're like, what is a root? It just is the x-intercept. So I'm going to use all those words simultaneously, okay? Now looking at this, guys, we were looking at quadratics. Now we are going to deal with things that are greater than quadratics today, but just making a point here. We know for sure it's going to have 2 solutions because of it. The highest degree is degree 2. Is that true? It's going to have 2 solutions, okay? Now remember that that's finding where we're crossing the x-axis here. There's going to be 2. Think about it. A parabola is a smiley face or frowny face. It's going to cross the x-axis twice. And then we did learn, well, what if it doesn't cross the x-axis? You can still solve the quadratic equation. It still has roots. It still has zeros. They're just going to be imaginary. So in something like this, people will graph it and say, well, it doesn't cross the x-axis, so it's no solution. Not true. We know that we can take a quadratic equation. We can solve by using the quadratic formula, right? And then sometimes we get imaginary roots, right? When we have a negative under the square root. Does that make sense, everybody? Okay. Awesome. Now, how we did this a lot of times, now I don't want you taking notes right here. I just want you looking, okay? This is just an example of what we've done so that you can understand what I'm doing here, okay? In a second, okay? So recall if a quadratic is factorable, you can, instead of using the quadratic formula, you can solve the quadratic by factoring. So look at what I did here. So I chose to use factoring to find the zeros. So I did what multiplies to be a times c, what multiplies to be a times c, which is 1 times 4, negative 4, and adds up to be b. This is how I learned how to factor. And then I did the factors. Now you don't need to take notes on this. I'm just showing you what we're doing here. Then we figured out, okay, this would have to be a negative 1 and positive 4 to add up to be positive 3 and multiply to be negative 4. So we knew our factors were truly negative 1 and positive 4. Then we did drop and break. So we took our quadratic, we dropped down the end terms, and then we broke down the middle term, rewriting it as our 2 factors. Is everybody following me? This is going way fast. I'm just recalling what we did here so that you can make a connection that I'm about to make here. Then we grouped these 2, we grouped these 2, and then we factored out of those what we had in common. So in this one I had an x, left me with x minus 1. In this one I had a 4, pulled out a 4, left me with x minus 1. Then we looked to check our safe haven. Safe haven, we're good. It's the exact same thing, sign and not everything, exactly the same. So then we can pull out our safe haven. To get here, we pulled out an x minus 1. So we divided out. That left me with x plus 4. Does everybody remember getting to that? Then we set our factors equal to 0. And the zero product property rule said we could set each of those equal to 0. So we split them up, setting that equal to 0, and setting that equal to 0, and then solving for x in each case. And we got 2 solutions. It crossed the x-axis at positive 1 and negative 4. So we went through all this process to find the x-intercepts. Now, what if we're given a function that's in this form? F of x is equal to x minus 1 times x plus 4. These are linear factors, right? Are they linear factors? So do we need to factor it? No, they're already done. There they are. It's already in linear factors. So we'd be going backwards if we started to multiply this together. If we did that, we would get x squared and all this sum thing. And then we have to go again and refactor it to get back to here. So you're being counterproductive by multiplying it through. It's already in factored form, guys. Look at it. It's already in factored form. So this one's going to have how many solutions? 2. Good. So once again, this is already in factored form. So we're going to set those factors equal to 0. So we have x minus 1 is equal to 0. And we have x plus 4 is equal to 0. And then we're going to solve for x in each case. So this one was easy because it was already factored. So I'm going to add 1. So I get x is equal to 1. That's one of my answers. That's where it's crossing the x-axis. So I'm going to graph that. I'm going to go over and put a point at positive 1. Questions on that part? Now I'm going to solve for x over here. So I'm going to subtract 4 from both sides. So I get x is equal to negative 4. So we know it's also crossing at negative 4. Now, I would go ahead and type this into my calculator to see what it looks like because it says draw a graph. Well, let's just use our calculator because, well, we know it's quadratic, so it's just going to be a U, but let's use our graphing calculators to check this to make sure. So look, everybody, let me show you something cool. Pull up your graphing calculators. Now go to y equals. You don't need to type it in any different than what it was given to you as. It was given to you as x minus 1 in parentheses times x plus 4. Type it in exactly as you see it, and it will graph it for you. So I'm going to put parentheses. X minus 1. Was it x plus 4? I've already forgot. Because I'm thinking so hard about teaching. Was x plus 4? Okay. So x minus 1 times x plus 4. So I type in times x plus 4. Then I hit graph. And I can see what it looks like. So it's evenly symmetrical around those 2 points. So I'm going to draw it the best I can. Now, the reason I had to actually solve for the x-intercepts is because to the human eye, you might just try to count and guess, but you might be off a little bit. So to the human eye, you've got to actually, you can't just tell for sure. You've got to go through and use the zeros to solve, and then you can go ahead and draw it in. So for now, I just want a rough sketch. Doesn't have to be perfect. Something like that will work. Okay, questions on that? Let's do another one. Now looking at this one's trickier. So we have f of x is equal to x minus 1 squared times x plus 2. Guys, x minus 1 squared. We got to be careful with this one. Times x plus 2. This is super important. Everybody listen up. You can't just square x and square negative 1. That is not correct. What x minus 1 squared truly means is x minus 1 times x minus 1 twice. Does that make sense, everybody? I'm rewriting it, and then times x plus 2. Now, these are already in linear factors. Is that true? So now we know we can just set these equal to 0 and solve for x in each case. So we have x minus 1 is equal to 0. X minus 1 is equal to 0. And I have x plus 2 is equal to 0. How many roots am I going to have? How many roots am I going to have? 3. So this is going to be degree 3. Interesting. That was just a side fact. So add 1 to both sides. So I get x is equal to 1. That's one of my answers. And I'm going to add 1 to both sides. X is equal to 1. So it's crossing out 1 and 1. Again, crossing again. And then we're going to subtract 2 from both sides. So x is equal to negative 2. So I'm going to go to 1. X is equal to 1. Now, it can technically cross through it twice. We'll use our graphing calculator to get the logistics here. So I'm going to put a point at 1 and negative 2. But then I've got to go to my graphing calculator and graph this to see what it looks like. So we have x minus 1 squared times x plus 2. So I'm going to pull out my graphing calculator here. So I go to y equals, and I'm going to type it in exactly correct. So I'm going to type in x minus 1 squared. Or you could type in x minus 1 times x minus 1. It doesn't matter. And then times by x plus 2. X plus 2. Then I hit graph. So notice it goes up through our point negative 2, then it comes down and it bounces on 1. It bounces on 1. Now the reason it bounces on 1 is because we got 1 twice. So it touches down and bounces back up. But really, if you have your graphing calculator, you can see what it looks like. You know the points are at negative 2 and 1, so just draw the graph accordingly. So I saw that it looked like this. It came up, and then it came and bounced down, and then back up. So that's what my graph looks like. Today we'll let you stay pretty rough in your sketching. Now this is something to understand before we get to the future stuff that we're going to learn here in a second. Notice how we got x is equal to 1 twice. Does everybody see how we got x is equal to 1 twice? This would be considered having 1 root, but it has a multiplicity of 2, meaning it happened twice. We got the root x is equal to 1, but we got it twice. So we would say x is equal to 1 with a multiplicity of 2. So you might get that. It's going to ask, that would just be good for later on. Anyways, just keep that in mind. X is equal to 1 with a multiplicity of 2, meaning we got it twice, and x is equal to negative 2. That was our answers to this solution. All right, so go ahead and use that information to now do problems 4 through 9 on the worksheet. You're just graphing. So it's already factored, guys. Set your factors equal to 0, and then use your graphing calculator and fill in the rest. Ready, set, go. If you're drawing parabolas, make sure you're drawing nice round things, because we're going to be dealing with this, in this class, we're going to be dealing with absolute value functions, and those are sharp B's. So they look similar, but they're very different. So make sure if you're dealing with a quadratic, meaning anything x squared, you draw a nice round U. So that's me being nitpicky, but in secondary 3 we have to. Also be careful not to misinterpret something like such as, okay, looking at something like this, for example, you'll set all your linear factors equal to 0. So you've got to set x equal to 0, and you've got to set x minus 5 equal to 0, and we know that x minus 5 squared is x minus 5 and x minus 5. So we would have something like this in this case. So really this one has 3 roots. So don't forget that this x is there. That's still a linear factor. Technically, that's really x plus 0. So technically, that's still a linear factor. So we have x is equal to 0 in something where you just have an x. So don't forget about that x. Very important. Still there. Okay, so hopefully you guys are able to see when you're given a function, it's kind of easy, especially if it's already factored into linear factors, to graph it, because you can just solve for those linear factors. You can solve for x, taking those linear factors and setting them each equal to 0, so you know exactly where it's crossing the x-axis, and then you can fill in the rest by using your graphing calculator. Now, we're going to be working backwards. So now this time, everybody look, this is super important. I promise you're going to see this the rest of the year, and I promise you'll see this on the quiz on Friday. So it says, now this time it says, we're given the roots, what's the polynomial? Now, once again, it says, given the roots, what's the polynomial? So think about it, guys. This time we're given the answers, and we're going to work backwards to get the polynomial. So we have to kind of think backwards on this. Now we can, I promise you can do it. Because if you think about it, to get to here, so we have x is equal to 2, and we have x is equal to negative 3. Now let's think backwards here. To get that from this side of the equation over here, we had to bring it over, right? And to get this 2, it used to be over on this side. To get it over there, you had to bring it over to here. And you had to do that using the correct operation. Is that true? Is that true? Yes. So let's work backwards, and let's use the correct operations and work backwards here. So if this is positive 2, we need to get this set equal to 0. We're working backwards. What should I do to get this equal to 0? Good. Subtract 2 from both sides. Now everybody pay close attention to what I'm about to write. On the left, I have x minus 2, true? And on the right, I have it equal to 0. That's where our linear factors began, right? And then we brought the 2 over this way. Does everybody see how I went backwards now? Okay, let's do it over here. So what do I need to do to bring 3 over? Add 3 to both sides. So on the left, I will have x plus 3, and now on the right is equal to 0. Does everybody understand what I did there? Working backwards. Okay, now think about what we did before we split these up. We had them multiplied together, right? They were multiplied together before we split them up and set them each equal to 0, right? Does everybody remember that? So now, let's bring them back together. And you've got to put them in parentheses. So we have x minus 2 times x plus 3. Before we split them up, we were here. Is that true? So I'm bringing them back together. Does everybody see that? Okay? And now from here, we can figure out the polynomial by actually multiplying it through. Because to get here, we had to factor. To get here, we had to factor. Well, we're going backwards of factoring, and that's multiplying everything through. So let's go through and do that. X times x is x squared. It's called double distributing, guys. X times positive 3. Now, I suggest always drawing in these arrows. X times positive 3. Positive 3x. Now I'm going to focus on my negative 2. I'm going to focus on my negative 2. Negative 2 times x. Negative 2x. And then negative 2 times positive 3, negative 6. So we're almost there. We've almost figured out the polynomial that had these roots, that had these answers. We're almost there. We got to combine like terms. So we have x squared. What's 3x is minus 2x is careful. 1x, so I'm going to write plus x. We combine those, we get plus 1x or plus x. And then we have minus 6. So guys, awesome. We went backwards. If we would have been given this polynomial and factored it all the way down, we would have got these answers. We went backwards. Does everybody understand that? One more, and then I'm going to set you free to try it on your own. One more, and then I'm going to set you free to try it on your own. It might be worded differently, so I worded this one how you might see it differently. Find the polynomial of least degree with these roots. So once again, this one's a little bit harder because we're going to have to multiply 3 together, but let's go through it. Find the polynomial of least degree with these roots. So these are the solutions, guys. These are the solutions here. X is equal to 2, x is equal to 2, and x is equal to negative 1. So I'm going to rewrite that a little bit prettier so I can just work backwards. So I have x is equal to 2. I also have x is equal to 2. And I also have x is equal to negative 1. I'm going to split it up so I can work backwards the way I did in that last example. So now to get this set equal to 0, I'm going to subtract 2 from both sides. So on the left, I have x minus 2 is equal to 0. Does everybody see what I did there? Subtract 2 from both sides. Subtract 2. So that leaves you with x minus 2 is equal to 0. That adds up to be 0, 0, just so you know where I'm getting the zeros. I'm going to add 1 to both sides. So now I have my linear factors. X plus 1 is equal to 0. Before we split them up, we had them together. The zero product property allowed us to split them up, but we can pull them back together. So we'll have x minus 2 times x minus 2 times x plus 1. Now we have to go through, is equal to 0. That whole thing is equal to 0. Now we have to go through and multiply all these things. Guys, we haven't seen this for a long time. So I need you all watching because most people make their errors here. And it would be a shame to get this far and make an error. So let me make a suggestion to you. Take my suggestion. If I see you doing it different, I'm going to tell you to stop and start over. Because you're going to make errors if you don't. This is my suggestion. Focus on multiplying 2 of them together. Simplify that, and then multiply the third one in. There are so many less errors, I promise. Guys, I have a math degree. I've practiced this a lot. This kind of thing a lot. I'm trying to help you. So take my suggestion. Focus on 2 of them, multiply them together, and then multiply the third one together. So let's go focus on this and multiply it out. X times x. X times x. Properties of exponents. X squared. Okay, good. And then we have x times negative 2. Negative 2x. Very good. And then we have negative 2 times x, which is negative 2x. Very good. And then, guys, careful. Negative 2 times negative 2. Positive 4. Very good. So then from here, before you multiply them in, simplify it, combine all like terms. Now, careful, guys. Think before you act. What's negative 2x's minus 2 more x's? Negative 2x's, guys, minus 2 more x's. Negative 4x's. So I have x squared minus 4x plus 4. Does everybody understand how I got here? Okay. Now I'm going to throw parentheses around that and not forget that I have to multiply in my x plus 1 here. I promise you'll make less errors if you do it this way. So now we've got to be really careful. We've got to distribute these things through to everything. Let's focus on x, guys. Now I would go this way. I would do these two because it's easier not to miss anything if I focus on these and multiply them in. But I'm going to focus on x and multiply it through to each thing. So x times x squared, can I come up here for a second? X times x squared. X cubed, which makes sense, right? We have how many solutions? 3, so it's going to be a degree of 3 in the end. Now x times negative 4x. Negative 4x squared. Good. Negative 4x squared. And then I have x times positive 4. Positive 4x. Now I'm going to distribute the positive 1 through 1 times x squared plus x squared. I wish I had more room to stay in line, but I'm not going to. 1 times negative 4x. Negative 4x. Good. And then 1 times positive 4. Positive 4. Then let's combine all like terms. So focusing on my x cubes, I only have 1 x cubed. So I have x cubed. Just took care of that. Negative 4x squared plus 1x squared. What do we get? Negative 4x squared plus 1x squared. Negative what? 3x squared. Good. So I add combining like terms. And then positive 4x minus 4x. Positive 4x minus 4x is how many x's? How many x's? 4x minus 4x is how many x's? 0 x's. So I'm not going to write that. That's 0. And then we have plus 4. So guys, this is a polynomial that had these solutions, had these zeros, had these x-intercepts. We went backwards. Questions on that? You have questions, guys. Careful when multiplying cubics. It would be a shame to know what you're doing and make an error. So be really careful when multiplying cubics. Okay, I'm going to give you a second to practice 10 through 13. Ready, set, go. One last time, guys. I'm telling you, we have a lot to learn every day, and this isn't review, so I'm telling you. Okay, now this is pretty quick. It's a pretty quick. I just want to make sure you're good to go with these ones so that you can go home and do this homework and be successful on it and have no questions, okay? So now it says, find the zeros and state the multiplicity of multiple zeros. Now, what I want you to understand is we're lucky because today I'm giving you ones that are all already factored. So looking at this, we can easily find the zeros, right? And we can then state their multiplicities. So looking at this, don't forget, guys, this is x minus 3 squared means x minus 3 times x minus 3. And we've already seen an example like this pretty much. and then we have x minus 1. Now, those are our linear factors, so we know by the zero product property rule, we can split those up, set them each equal to 0, and then solve for x. And then we have x minus 1 is equal to 0. Then solving for x in each case, add 3 to both sides, right? X is equal to 3. Interesting. Add 3. X is equal to 3. And then I'm going to add 1. X is equal to 1. Now here's the important part, guys. You have to write this correctly. So it says state the roots and then state their multiplicities. So this is how you write it. X is equal to 1. It only happened once, so that's all you have to write. X is equal to 1. Then we have x is equal to 3. You can't write it twice. Now that we're in secondary 3, we expect you to understand multiplicities. So you would write x is equal to 3 with a multiplicity of 2. Because that means it happens twice. 3 happened twice. So we got x is equal to 3, yeah, and we got it twice. So you write x is equal to 3 with a multiplicity of 2. So what if that happened 5 times? What if we had x minus 3 to the 5th? How many times would it have happened? 5, right? So we would have got x is equal to 3 5 times. So we would say x is equal to 3 with a multiplicity of 5. Does that make sense, everybody? Yes? Are we sure? Do we need another example like that? Okay. Are you sure? Okay. Awesome. So you guys finish up the worksheet. It's due tomorrow. Do not put anything away. We still have 10 minutes, and we have like 6 minutes. I want you working till the end of the hour, because I know for a fact you're not finished, okay? Work till the end of the hour, please. Thank you. So on the problems where it says that most calculators, so for problem 18, it says most calculators won't graph functions unless they are in the form y equals some expression involving x. Rewrite the functions below to be in that form. So look at part A. We have x is equal to 3y plus 6. Now, once again, it says that we need to rewrite this in the form y equals some expression involving x. So what we're ultimately trying to do, you guys, is we're just trying to get y all by itself. So what I'm going to do is I'm going to subtract 6 from both sides. So over here on the left, that leaves me with x minus 6, which is equal to 3y. We can't combine x and negative 6. They're not like terms. So then from here, I would get y alone, and we'll divide both sides by 3. Make sure you divide that entire side by 3, because if you don't, you haven't done it correctly. So now we really have y is equal to, and then we have x minus 6 over 3. Now notice I have it in the form y is equal to some function involving x. I have it y equals x minus 6 over 3. So that's in the correct form. If you type that into a calculator, it would graph it. But if you tried to type in this, x is equal to 3y plus 6, you couldn't do it. So now here, we could type that into a calculator. So I'm going to do B, and then I'm going to let you finish the rest of those ones on your own. So I have x is equal to, well, I'm not going to do, you know what I'm going to do? Because this one's harder. I'm going to do problem D. So if you look at D with me, I have x is equal to 2y squared minus 4. So what I'm going to do is solve for y piece by piece so I can get it in the form y is equal to some function involving x. So I'm going to add 4 to both sides. So then I have on the left x plus 4 is equal to 2y squared. We're trying to get y completely by itself. So I would divide both sides by 2. So we have x plus 4 all over 2 is equal to y squared. Well, y is not by itself. That's y squared. But we have talked about this, guys. To undo a square, something squared, the inverse of something squared is the square root. So we're going to take the square root of both sides. You can't just do it to one side. So on the left, I have the square root of all that stuff, x plus 4 over 2. And then on the right, our root cancels out with our power, and that leaves us with is equal to y. So now notice y is all by itself. And we've done this piece by piece. So essentially, what we've done here essentially is we found the inverse of this function, but we'll get into inverses later on. But that's what we've done here is we found the inverse. Okay, so now y is all by itself, and we should be good with the rest of those. There were some tricky ones. Be careful with E, because before you can add 5 to both sides, you've actually got to square root both sides, because notice the y minus 5 is in the square, is in the parentheses. All of that stuff is in parentheses raised to the second power. So before you add 5 to both sides, you've got to take the square root of both sides. And then that undoes the power of 2, and then add 5. Be careful with that one. If you need help with that one, come in. And then don't forget, looking at 19, to be really careful because there's a difference between f of 0, this is on 19, f of 0 and then f of x is equal to 0. There's a difference. So with f of 0, you're going to be plugging in a 0 wherever there's an x. So we'll be doing 2 times 0 minus 7. And then in f of x is equal to 0, that would be 0 is equal to 2x minus 7 because that is saying f of x is equal to, and we plugged in for f of x are 0. So then from there you would solve for x by adding 7 to both sides and so on. I'm going to let you finish that one. And then once again, I'm looking at 20, problem 20 really quick. Looking at problem 20 here, it says, algebraically determine the y-intercept of each function. Write each answer as an ordered pair. So I'm going to do problem A. So we have y is equal to 3x plus 6. So we want to find the y-intercept, guys, and that's where it's crossing the y-axis. So we think about an xy chart here, and we have a, like, example, this is a line, and it's crossing at positive 6 with a slope of 3. So it looks like that. It's crossing, okay, so the x is asking for the y-intercept, which means where it's crossing the y-axis. Now you could do this algebraically if you think about it, guys. Right there on y, when it's crossing the y-axis, our x is equal to 0. Right there is 0 on our x-axis. So if you plug in a 0 for x, that's always going to be your y-intercept. So we have y is equal to 3 times 0. You plug in a 0 for x to find the y-intercept, because think about it. When it's crossing the y-axis, our x value would be 0. Once again, I'm just clarifying that. So 3 times 0 is 0 plus 6. So our y-intercept is 6. So for all the functions, like problems B, C, D, E, you can just plug in a 0 for x, plug in a 0 for x, and that will give you the y-intercept. Your function at 0 is going to be your y-intercept. Also be careful on part B, because notice it's not in the form y is equal to. You need to fix it, and we did that in problem 18. So fix it first, get it into the form y equals something, and then plug in a 0 for x, okay? And that's for part B of problem 20. All right, hopefully that helps you for anyone that was struggling on those pieces of it. And have a good day. Thank you for watching.